Are some infinities bigger than others? In the late 1800s, Georg Cantor was really the first mathematician to formally explore these ideas and to formally prove that, yes, there are different sizes of infinity. The term cardinality in mathematics is used to refer to the size of a set. The cardinality of a finite set is the number of elements in that set. And this allows us to make statements like this first set here is a larger set than this second one because it has more elements, it has a greater cardinality. In order to extend this comparison of the sizes of two sets to infinite sets, we think about pairing elements of the first set with elements of the second set. And if we can do this in a way where nothing is left over, we'll define those two sets to have the same cardinality. In this example, we see that the first set has elements left over, and so we'll define it to have a larger cardinality. This pairing of elements we might call a one-to-one correspondence. As a reminder again of some definitions, we say that a function f from x to y is one-to-one if f of x1 equals f of x2 implies x1 equals x2. I suppose you could equivalently think about this as x1 not equal to x2 implies that f of x1 is not equal to f of x2. In other words, one-to-one means that different inputs yield different outputs. This is also called injective, and the function f is onto or surjective if, given any y in y, there exists an x in x such that f of x is y. So every element of the codomain is actually achieved by the function. Looking again at that first example, if you think of this as a function pairing elements in this lower set with elements in this upper set, this function would be one-to-one, but not onto. In this example, we have both of those conditions, in which case we can call this a bijective correspondence or a one-to-one correspondence. Even though that function in the first example was one-to-one, we wouldn't call it a one-to-one correspondence between the two sets because there's not a one-to-one function both ways. So now we can write down that definition of what it means to have the same cardinality using this terminology. The set x has the same cardinality as y if there exists a function from x to y that is one-to-one and onto. And we can denote that as x tilde y, meaning x has the same cardinality as y. And while it still might be unclear what we mean by the cardinality of an infinite set, we can at least talk about when two infinite sets have the same cardinality. The canonical first counterintuitive example is that the even numbers have the same cardinality as the naturals, because these two sets can be put into a one-to-one correspondence. The function that maps 1 to 2 and 2 to 4 and 3 to 6 is a bijection. So letting e denote the set of even numbers, we could write this, saying that the naturals have the same cardinality as the even numbers. And it is true that the even numbers are a proper subset of the naturals. And so you could argue that in some sense they have a smaller size, but this way of thinking about size is not super helpful and is mostly influenced by the amount of time we spent with finite sets. These have the same cardinality. In a similar way, we can show that the naturals have the same cardinality as the integers. To demonstrate this, we'll either need a bijective function from the naturals to the integers or from the integers to the naturals. Let's do that first technique, and let's define f of n to be n minus 1 over 2 if n is odd, and negative n over 2 if n is even. Then 1 goes to 0, 2 goes to negative 1, 3 to 1, 4 to negative 2, etc. And this is one-to-one because we don't see any repeated outputs, and this is onto because every integer is going to show up in this list of outputs. And this is not the only function that would make this work. Let's look at another example of two sets with the same cardinality, the interval negative 1 to 1 and the whole real number line. There's a number of ways to show this, but consider the function f from the reals to the interval negative 1 to 1, defined by f of x equals x over 1 plus the absolute value of x. And also consider the function g from negative 1 to 1 to the reals, defined by g of x equals x over 1 minus the absolute value of x. I won't go through the algebra here, but you could show by composing these functions that these are inverses of one another. And you could argue that that forces f to be a bijection. And so those two sets, its domain and codomain, have to have the same cardinality. And by engineering a function to shift and scale an interval, you could show that negative 1 to 1 has the same cardinality as any interval a to b, where a is not equal to b. And this notion of has the same cardinality as is an equivalence relation. It satisfies the properties of reflexivity, symmetry, and transitivity, just being fancy words to say that a set has the same cardinality as itself. If A is the same cardinality as B, then B has the same cardinality as A. And if A is the same cardinality as B, and B is the same cardinality as C, then A is the same cardinality of C. And that transitivity allows us to conclude that any interval A to B has the same cardinality as the set of all real numbers. Seeing all these examples of pairs of sets that maybe counterintuitively end up having the same cardinality A natural question would be, do all infinite sets have the same cardinality? Is there just one size of infinity? We've shown that the naturals have the same cardinality as the even numbers or as the integers. Maybe they have the same cardinality as every infinite set. We'll define a set X to be countable if the naturals have the same cardinality as X. The reason this is called countable is because if the natural numbers can be put into one-to-one correspondence with our set X, then it's like we could count the elements of X. There would be a way of enumerating all the elements. An infinite set that is not countable is called an uncountable set. With these two new definitions, our question becomes, are there any uncountable sets? And our answer is going to be yes. And the way I'm defining the terminology is very suggestive of that. But it's not an obvious result. Before jumping straight to trying to find a bijection between the naturals and the reals, or proving that no such bijection exists, let's consider the set of rationals. So as a theorem, the set of rational numbers is countable. And this is maybe even a little bit more surprising than the fact that the integers or the evens were countable. What this means is that the rationals can be put into one-to-one correspondence with the naturals. The key observation that will allow us to do this is that every rational number has a unique expression as some plus or minus p over q, where p and q are in lowest terms. Let's set A1 to be the set containing 0, and then for each n greater than or equal to 2, let's let an be this set of all plus or minus p over q, where p and q are natural numbers in lowest terms, meaning they have no common factor, with p plus q equal to n. We can list out the first several of these sets. A2 contains 1 over 1 and negative 1 over 1. A3, 1 over 2, negative 1 over 2, 2 over 1, negative 2 over 1. A4, A5, etc. And every rational number is going to show up in exactly one of these sets, and each of these sets is finite, because there's only finitely many ways for two numbers to add to n. So we'll construct our bijection, our enumeration of the rationals, by taking all of the elements in each of these sets and forming a list in order, where we start by listing the element of A1, then list the 2 elements of A2, then the 4 elements of A3, etc., etc. And if we wanted to make this even more explicit so that we know exactly what each natural number was paired with, we could describe some canonical way to order the elements within each set, or even formalize things further by coming up with an algorithm that takes in a natural number and maneuvers through a grid of the rational numbers, explicitly charting out a path that hits each rational number once. And that's a good exercise to do, but it would be too much of a tangent from our main conversation, so I won't go through that here. We'll move on to our main result, which is that the set of real numbers is uncountable. In other words, it's impossible to find a bijection between the naturals and the reals. It wasn't the first way that he proved this result, but Cantor's most famous proof of this result is a diagonal argument. He used binary digits, but let's just continue to work in base 10. We've already shown the reals to have the same cardinality as any interval. So let's look at the interval from 0 to 1. Every real number in that interval has a decimal expansion. We could put a decimal point and then write an infinite sequence of the integers 0 through 9 to represent that number. Now, proofs that a set is uncountable are generally contradiction arguments. So let's assume toward a contradiction that there exists some way to enumerate all the real numbers between 0 and 1. That there exists some map from the naturals to the interval 0 to 1. And that would allow us to write them all out in a list like this. I'm just putting chaotic looking numbers here because who knows what the ordering is, but there would be some way of doing this. But then Cantor says, I'm going to come up with a number that can't be on that list. I'm going to form a new number by making sure its first digit is different than the first digit of the first number, and its second digit is different than the second digit of the second number, and its third digit is different than the third digit of the third number, etc. And we could explicitly choose some way to make them different. Like, for example, you could say, replace the digit with a 3, unless it's already a 3, then make it a 4. And that would be one of many ways to construct this new number. And there's a reason to avoid using 0 and 9. But then Cantor could write down this number. And since two numbers can only be equal if they have the same decimal expansion, this number isn't on the list, which is a contradiction. Now, this argument has a few holes in it, and so we're going to do another argument that's a little bit more airtight. One issue is that claim I just made, that two numbers can only be equal if they have the same decimal expansion. That's not entirely true. If you think of some weird thing like 0.99999999999, that's equal to 1. Or you could do 0.0000, infinitely many zeros, and then a 1. So avoiding the numbers 0 and 9 as our digits helps resolve this issue. But it still is relying on that unproven result of the uniqueness of decimal expansions. So let's instead do this proof another way. And this time let's just work directly with the real numbers instead of the interval 0 to 1. We'll assume toward a contradiction that there exists a bijection f from the naturals to the reals. Letting x sub n denote f of n, we can write out this ordered list, and every real number has to show up on this list. In episode 4, we used the axiom of completeness to prove the nested interval property, and we'll use that here. Let's let I1 be some closed interval that does not contain x1, and we'll require that this is actually an interval with some length, that the two endpoints aren't just equal to each other, making it a singleton set. We can then define I2 to be some sort of closed interval contained within I1 that does not contain x2. And again, we'll require that its endpoints are not equal to one another. And we know such an I2 has to exist because we could definitely embed two disjoint closed intervals within I1, and x2 could belong to at most one of them, so we could take the other one. And we'll continue inductively for n greater than or equal to 3, defining In to be a closed interval contained in I sub n minus 1, such that xn is not an element of In. Now, by the nested interval property, the infinite intersection of all of these intervals is non-empty. So say it contains an element x. Then x lives in each of these intervals. Since x lives in I1, x is not equal to x1. Since x lives in I2, x is not equal to x2. And in general, since x lives in In, x is not equal to xn for any n, which means x is not on our list. But this list was supposed to contain every real number, so we've reached a contradiction. Thus, the real numbers are an uncountable set. An immediate corollary to this result is that the set of irrational numbers must be uncountable, because if the irrationals were a countable set, then that would make the reals a union of two countable sets, because we already proved that the rationals are countable, but the union of two countable sets is still a countable set, which contradicts the reals being uncountable. And I suppose we haven't yet proven that the union of two countable sets is countable, but next video will actually prove a much stronger result, that any finite union of countable sets is countable, and furthermore, any countable union of countable sets is countable. Now, we've used this equivalence relation, has the same cardinality as, to identify when two infinite sets have the same size. But it'd be nice to extend this further to make statements with inequalities about cardinalities. I'd like to be able to say that if there's a function f from x to y that's 1 to 1, then the cardinality of x is less than or equal to the cardinality of y. So we could say something like the cardinality of the naturals is less than or equal to the cardinality of the reals. And in that case, maybe it should be a strict inequality because we've proven that these can't be the same. Now, we won't go into formally defining these cardinal numbers or these sizes of infinities, but I will show you this symbol, pronounced aleph naught. This is the smallest cardinal number used to denote the cardinality of the naturals or any countable set. Any set whose cardinality is strictly less than this is finite. And then we said the cardinality of the reals is strictly more than this. So a natural follow-up question would be, is there any cardinality strictly in between? Can you construct a set whose cardinality is strictly greater than that of the naturals, so it's uncountable, and yet its cardinality is strictly less than that of the reals? And this question was not resolved in Cantor's lifetime. He believed that no such set existed, and this became known as the Continuum Hypothesis. In 1940, Kurt Gödel, famous for his incompleteness theorems, proved that from standard axioms in set theory, it's impossible to disprove this hypothesis. But then in 1963, Paul Cohen proved that under the same rules, it's impossible to prove this hypothesis. In other words, the hypothesis can be accepted as true or as false without contradiction. It's what's called an undecidable statement. In the next video, we'll continue proving a few more theorems about cardinality and discuss power sets and Cantor's theorem. And following that, we'll explore a very famously counterintuitive set, the Cantor set.